Chapter 8, Regression. After determining that a significant linear relationship exists between two variables, the data can then be used for regression. Simple linear regression, or SLR, involves modeling one y variable based on one x variable. Multiple linear regression, or MLR, involves modeling one y variable based on more than one x variable. The y variable is referred to as the dependent variable or the response variable. The x variables are referred to as the independent variables or the regressor variables. Regression can be used for modeling, estimation, or prediction. Using simple linear regression, we look for a line that follows the pattern of the data. In Figure 8.1, you can see that there are three possible lines to fit the data, but there is one, this red line in the middle, that best fits those data points. When we say best fits, we're referring to the minimum vertical distance between all points and the line. So each of these distances, if you take them, some of them are negative and some of them are positive. So if you square them all and make them positive and then find the average or find the sum, you're going to find that for the best fit line, those distances are the smallest that they could possibly be. So every other possible line that you could draw through these data points is going to yield a larger vertical distance between the points and those specific lines. In a mathematics class, you may have learned the equation of the line as being y equals mx plus b. The y represents your dependent variable. The x represents your independent variable. M represents the slope of that line, and b represents the y-intercept, which is the location of y where x is equal to 0. The population regression equation is very similar to the equation of a line. If you look at the two, you have very similar patterns. Here you have a single value, and here you have a single value. Here you have something that's multiplied by x, and here you have something that's multiplied by x. So in fact, this beta naught represents the y-intercept in the regression model, and this beta 1 represents the slope of the regression model. And that's all for the population. If you do a sample regression model, meaning that you find the regression model in this regression equation based on only a sample of data rather than the entire population, then you have this value b naught, which is an estimate of beta naught, and b1, which is a sample estimate of beta 1. So these are the values that you would be able to compute based on your sample. Note that if r is positive, meaning our correlation coefficient is a positive value, then the slope of the regression line will also be a positive value because the positive slope. Now let's look at the manual calculation of the sample regression coefficients, and we'll do so for illustration purposes only. I would never expect somebody to actually do this by hand because there are a lot of places where mistakes can be made in hand calculations, and the computer will do it easily for us. So if you look at this equation, this is the equation for the y-intercept, and here is the equation of the slope. So you have lots of products of x's and y's. In some cases they're squared, in some cases they're not. So what we have here is the x's and the y's. So these two columns represent our data. These other columns are used for, essentially we have here the x values squared, we have the y values squared, we have the x times y values, and then we have all those sums or those totals. So those are the values that you would be entering into these equations if you were going to compute them by hand. And we're not going to do that. We're going to look at how StatCrunch would do these automatically for us. So here we have our data, and we go to Stat and Regression, then to Simple Linear to do our simple linear regression. You can see that there are other options available with regression, but we're going to stick with the simple linear regression, which is the most basic. It asks us for the x variable and for the y variable, so we indicate that the x variable is the exam scores, and that the y variable is the final scores. Then we click on Calculate, and we get a lot of results here. It gives us an equation. Final is equal to 17 plus 0.81 times exam. That is our regression equation. So y is final, x is exam, 17 is our y-intercept, and 0.81 is our slope. You can see r, which is the correlation coefficient, as 0.959, which you may remember from the previous chapter. And you can see r squared, which is the coefficient of determination, which is 0.92. Down here we have a table of parameter estimates. So again, it gives us the estimate of the slope, which is 0.81, and the estimate of the intercept, which is 17. We then have these tests over here, which are essentially testing whether or not the slope is equal to 0 and whether or not the intercept is equal to 0. And we'll look at that at a later point. Residuals are the difference between the best fit line and the actual observations in the data. So if you recall in a previous slide, we indicated that the best fit line is the line such that the vertical distance between each point and the line is as small as it can be. Those distances are called residuals. The residuals are calculated as the difference between the actual data values y sub I and the value of the line y hat sub I. The residuals help us assess the fit of the line to the data. The assumptions with regression include linearity, independence, normality, and equal variance. The acronym LINE is helpful in remembering those assumptions. In assessing linearity, we are looking for a scatter plot of the data that follow a linear pattern. For independence, we're looking for independence among the observations, meaning there's nothing that relates one of the individuals to another individual that would have some type of effect on our model. For normality, we're looking for the residuals to follow a normal distribution. So there are a couple of ways that we can assess that, either with a graph or with a test, to determine if our residuals are in fact normally distributed or close thereto. With equal variance, we're looking at the variability in y being equal across all the values of x. So the spread of the data from left to right in our graph should be fairly similar in nature, similar in width. If the assumptions are not met, the regression analysis will not yield useful or accurate information. So let's take a look at how we would assess these assumptions. When the assumptions are met, linearity is going to give us a fitted line plot of x versus y that follows essentially a linear pattern. The residuals are going to be scattered in nature with no visible pattern. Here's an example where the assumption of linearity is violated. In this case, you can see there's clearly a curve in the pattern of x versus y. You can also see that in the residual plots, here's a curve, here's another curve, and here's yet another curve. So we're not finding linearity in this second situation like we did here. So again, for this first situation, these last three residual plots, you're not looking for a linear pattern. Even though we're testing linearity, you're just looking for a scatter that doesn't include any kind of curvature. We assess the independence assumption as part of the data collection process. If we use a random sampling process, typically it will take care of the independence aspect. The assumption is that each observation is independent of each other observation. And violations of the assumption might occur if each observation is, for example, multiple blood pressures taken on the same person. They're going to be related because they're all taken from the same person. Or measures of corn yield taken at numerous places in the same field. Because it's the same field, you would expect them to be related. Or heart rate measured on an individual over time during exercise. That heart rate may gradually be going up. They're all related to the same individual because they're taken on the same individual. So you're not getting independence in those different situations. The assumption of normality can very well be checked using different graphs. There is a histogram that you can create of the residuals, which should have somewhat of a bell shape to it. It may not be exact, but it should have somewhat of a bell shape to it. And there's also a normal probability plot, which in this case in StatCrunch it's called a QQ plot of the residuals. And what that is looking at is comparing the normal distribution versus the distribution of the residuals. So if they're the same, if they're both the normal distribution, then it should be like a 45-degree angle straight line. And so departures from that straight line would indicate departures from normality. So this is the two top ones are what the graphs look like when the assumption of normality is met. The two bottom graphs are what the graphs would look like if the assumption of normality is violated. So in this case, we have a skewed distribution of our residuals, and so you know that this is not a normal distribution. And here's a QQ plot of the residuals, which essentially is looking at normality across the horizontal axis and our residuals on the vertical axis. And you can see in the tails very clearly there is some curvature, and quite a bit of curvature. For the equal variance assumption, here are two graphs where the assumption of equal variance is met. You can see that there's just a big scatter of points, and there's no patterns that would indicate that the spread of the points is different anywhere along the x-axis. Same is the case for this graph. Now, for these others where the assumption is violated, you can see that there are patterns. In the first graph, the spread of the pattern seems to be that the points are spreading out more for higher values of x than they are for lower values of x. For the second one, you can see there's spreading out more, and then they're going back in narrow again. And for the third one, you can see they start spread out and narrow, and then they increase again. So the points here in the middle are less spread out than the ones on either end. And so equal variance is not taking place here because the variance is not equal all the way across. It's something smaller in the middle than it is on either end. And so any of these three cases would be clear patterns of a violation of the assumption of equal variance. Whereas the others, if you don't see a pattern, if they seem to just be kind of equally spread out everywhere, then you would assume that the assumption of equal variance is met. So essentially we're saying it's met unless we can see patterns that would cause us to think otherwise. We can use the regression equation for predictions. The final grades data sample regression equation is as follows. This is what we got from the output, recall? And so the y hat represents the estimated response or the overall final grade. In the output it said grade here. And x represents the actual exam grade, which in the output it listed as grade. For a person with an exam grade of 80%, for example, you can put the exam grade of 80% in for x. Notice that we're using 80 and not 80% or 0.8. If we were to use 0.8, then we would have to base our model off of percentages as well. Recall that the data used in creating the model appeared in the same format as this 80. So you have to use the same format for the value you enter for x. That also means that when we interpret the results, we have to interpret the results in that same fashion. So when we plug in the 80 into our regression model for x, we multiply it by the 0.81, and then we add that product to 17.2685, then we get 82.4365 or 82.4%. There's also a caution not to extrapolate. What that means is if we go back to the data that we used to create our regression model, we have values here in the 70s, 80s, and 90s. And so we don't know what would happen if we were to get values of x that were in the 40s or 50s, say. It could be that they would follow the same linear pattern as our regression model, or it could be that they wouldn't. So extrapolation would be trying to put in for x a value in the 40s or 50s when our model was based on values in the 60s, 70s, 80s, and 90s. It may not work appropriately. We created our regression model with values in the 60s, 70s, 80s, and 90s, and so that's all we know that it's going to be good for. It may not work for values in other ranges. Consider these graphs of the world record 1-mile sprint for women. If you look at the 1960s to the 1980s, the records fit this very nice linear pattern. So you might be tempted to predict, using this model, what the world record might be in 1990 or in 2000 or 2010. Or you might be tempted to predict what a world record might have been back in the 50s or 40s or 30s. But it would be hazardous to use this model to predict values that are outside of this range of 1960 to 1980 for which this linear pattern exists. Let's take a look at what happens after 1980. If you notice, there's actually a leveling out of the pattern. If you think about it, the world records are not going to continue to drop at a linear rate. In fact, if we were to extrapolate, we would predict that in the year 2212, the world record would be less than 1 second for running a 1-mile sprint, and in 1812, the world record would have been 7.7 minutes. Now, although the 1812 figure looks like it could be reasonable, the 2212 world record estimate does not. There is variation in our regression model. The difference among our observed responses, y, the average response, y bar, and the best fit line, y hat. The total variability is considered the difference between the individual responses and the average response. We can break that total variability into two different components: explainable variability and unexplainable variability. The explainable variability is the variability that is due to our model. So there's a difference between the data we observed on average and our model, which is our regression line. It's called explainable variability because it's made up of our x value, which is the value that we use for our independent variable that we assume is going to be influencing our dependent variable, which is y. The unexplainable variability, which we call random variability, is the difference between each individual value and the model y hat. That is the variability that exists in addition to the variability that we can explain with our model. So we're using x to try and explain y, but even with x, there is still some difference in our observations and how they differ from our line that we can't explain just by x. Because what we explain with x is our regression line, and the points don't fall on the regression line. If they all fell on the regression line, then the variability would all be explained by x. But because they don't, there's something else going on there. We call it unexplainable, but in many cases it's just random variability. It's just the fact that in nature and in life there are differences. But if we're able to find and quantify what the differences are that are affecting the outcome, our y variable, then we can use those as additional x variables or additional independent variables and help explain more of our variability in our data. The coefficient of determination was introduced earlier as the proportion of the total variability that is explained by our regression equation. It is denoted r squared, and it can be computed by taking the correlation coefficient and squaring it if you have only one independent variable and one dependent variable. With regression, that's what you would get in the case of simple linear regression. In multiple regression, you have multiple x values and a single y value, and so you can't compute a single correlation coefficient that accounts for the entire model. So the coefficient of determination is computed a different way. And essentially what it amounts to is the explainable variability divided by the total variability. And so it's essentially telling us what proportion of the variability is explainable by our model. When that value is close to 1, it indicates that our model fits very well the pattern of the data. When that value is small or close to 0, then it indicates that there's more going on there in the unexplainable variability than there is with the explainable variability, meaning that our model is not accounting for as much as we would like. So we're not capturing the phenomenon that is causing the variation in the data. In summary, simple linear regression involves modeling one y variable based on one x variable. The best fit refers to the minimum vertical distance between all points and our best fit line. Residuals help assess the fit of the line to the data. Our assumptions are linearity, independence, normality, and equal variance. Regression equation can be used for estimation and prediction, and the coefficient of determination can be used to quantify the fit of the data to the model. And that is the end of Chapter 8, Regression.